Hello. I will introduce our recent work, Open-o3 Video, a unified framework for grounded video reasoning with explicit spatio-temporal evidence. Recent video reasoning models such as video, R1 and video RFT use reinforcement learning to enhance reasoning. However, they only generate text-based reasoning traces, without showing when and where the key evidence appears. Inspired by thinking with images like Open-o3 and Deep Eyes, we extend this paradigm to videos. Videos are dynamic, containing moving objects and scene transitions. We aim to retrieve key frames and regions that align with the reasoning chain, enabling the model to truly reason with the video. However, we face three main challenges. 1. Lack of reasoning datasets providing joint spatiotemporal supervision. 2. Difficulty of optimizing models to localize objects across time and space simultaneously in complex scenes. 3. How to maintain strong video QA ability while enhancing grounding, and how to leverage the spatiotemporal evidence to improve inference via test time scaling. To fill the data gap, we built two datasets, STGR COT30K for supervised fine-tuning and STGR L36K for reinforcement learning. They combine temporal-only and spatial-only sources with 5.9K newly annotated spatiotemporal samples. Each example includes a question, answer, keyframes, bounding boxes, and reasoning linking them. We use Gemini 2.5 Pro for annotation, Qwen 2.5 VL for box verification, and strict consistency checks to ensure data quality. Our training follows two stages. Stage 1. Cold start initialization on STGR COT30K equips the model with basic grounded reasoning. Stage 2. Reinforcement learning with group sequence policy optimization stabilizes long horizon optimization. The total reward equals format reward plus accuracy reward plus thinking evidence reward. A major challenge in video grounding reinforcement learning is that spatial rewards rely on accurate temporal predictions. Bounding box IOU is meaningful only when timestamps are correct. To overcome reward sparsity, we propose two mechanisms. Adaptive temporal proximity gradually narrows the allowed time gap between predicted and ground truth timestamps, providing dense feedback early and enforcing precise alignment later. Temporal gating activates spatial rewards only when temporal predictions are sufficiently close to ground truth, preventing irrelevant objects from being rewarded. Together, they ensure smooth optimization and coherent spatiotemporal alignment. As for reward design, specifically, accuracy reward is for correct answers and IOU alignment. Thinking reward consists of a temporal term and a spatial term. Format reward encourages correct use of specific tags. These mechanisms ensure stable and interpretable spatiotemporal grounding. In addition, the explicit evidence traces can support evidence-aware test time scaling. At inference, we generate N responses. Each response contains spatiotemporal traces. We crop those regions and recheck their relevance to the question. And the final prediction uses confidence-weighted voting according to the feedback score. This confidence-aware scaling reduces hallucination and improves robustness compared to simple majority voting. On the V-star benchmark, Open-o3 Video achieves state-of-the-art results. It improves over Qwen 2.5 VL by 14.4% in MAM and 24.2% in MLGM, surpassing GPT-4o and Gemini 2 Flash. The model effectively grounds both temporal and spatial evidence, delivering accurate and verifiable reasoning. Across Video MME, WorldSense, Video MMMU, and TVG Bench, while providing more intuitive spatiotemporal evidence, our model achieves comparable or even superior results to other video reasoning models, especially on long videos and temporal localization. Ablation studies demonstrate the superiority of our training strategy. Both adaptive temporal proximity and temporal gating contribute clear gains, high-quality spatiotemporal data are essential, and confidence-aware scaling consistently delivers better performance. Here we show some qualitative results. Our model not only answers correctly but also highlights the exact frames and regions supporting the reasoning. For example, identifying a spotted cat, or showing a bunny attacking the cameraman. The demo video further visualizes timestamps and boxes appearing as the model reasons through the scene. To conclude, Open-o3 video introduces explicit spatio-temporal grounding into video reasoning. Through curated data, adaptive GSPO training, and confidence-aware inference, it significantly enhances both accuracy and interpretability. In future work, we plan to extend to longer and more complex videos, include audio cues for more transparent multimodal understanding. Thanks for your watching.